All right, it's time for us to start the last bit of Physics 20, the last part of the last unit. So we are going to look at mechanical waves. So we're going to look at longitudinal and transverse waves, we're going to look at the universal wave equation, we're going to talk about reflection, interference, acoustic resonance, and finally the Doppler effect. So let's get into it. When you hear the term wave, you're probably thinking something like this, like a surfing wave, and you'd be correct. That is certainly a wave. And we want to ask ourselves more generally, what is a wave? Well, a wave is just an oscillation, or we could say it's a disturbance, and it causes a transfer of energy through a medium. So all a wave does is it takes energy from one place and moves it to another. So it just transfers energy. One of the big things we want to be really careful with is that a wave only transfers energy. It does not actually move matter. So when we look at this water wave, we might think, well, the water itself is moving. Like, like if the wave's kind of going this way, we think all the water is moving that way. And that's not actually true. The energy transfer is heading that way, but the water itself is not doing that. Like if we kind of have, and I'm going to sketch this here. So if we have like water molecules, now it may seem like the direction of the wave appears to be that way. The direction of energy transfers that way. But what you'll actually notice is that the water molecules, they just oscillate about an equilibrium position. So like these waves are just these molecules are just going to kind of oscillate up and down, and they're going to transfer energy in this direction. So a wave is really just a fancy way of executing simple harmonic motion. That's all it is. That's why we talked about SHM before we got into waves. Now, we are going to look at mechanical waves. That's kind of our focus. And these waves are waves that need a medium to propagate. A medium is just a means for that wave to actually be able to travel. So for example, if you'd like to have a water wave, you need to have water. Water would be the medium. If you'd like to have sound, you need to have air. Air is going to be the medium. In Physics 30, if you do take that, you're going to talk about a special class of waves that do not need a medium to propagate. These are what we call electromagnetic waves. So things like light, X-rays, gamma rays, all those fun things, those fall under the electromagnetic radiation spectrum. What's special about electromagnetic waves is that they, in a vacuum, they always travel at what we call the speed of light, which we denote by little c. The little c is for celeritas, which is Latin for quickness. So the accepted value for the speed of light is 299,792,458 meters per second. That's a lot to remember, and it's a heck of a mouthful. So for us, 3 times 10 to the 8 meters per second is going to be just fine, and that is located on the data sheet, so please do not memorize that number. We will use it a little bit in this unit. So when we're looking at waves, we do have some terminology we want to throw in. The important ones, so equilibrium is kind of our undisturbed resting position of the wave. And then we're going to have our amplitude, which is the greatest displacement from equilibrium. This hasn't changed from simple harmonic motion. So we have this wave here, it's displaced from equilibrium, comes back down. This is our greatest displacement from equilibrium. So this is what we refer to as our amplitude. And we can look at either above or below the equilibrium, doesn't matter. So our highest point of the wave, at this point here, this is referred to as a crest. The lowest point, this is referred to as a trough. The big one that you want to know about is this wavelength. So the wavelength represents a complete cycle of the wave. The easiest way to deal with that is to go from one peak to the next peak, or one crest to the next crest, or one trough to the next trough. That is my recommendation, because sometimes people go one equilibrium to the next equilibrium point, but the problem is from here to here, that's not a complete cycle, because we have to do a whole up and then a down. So like this distance here, that distance would be my wavelength. So I would always say, if you're trying to calculate wavelength, go from crest to crest or trough to trough. That is your best bet. So like here we have like a trough to trough. So like that distance there. That's my recommendation. So it is denoted, the wavelength, by this Greek letter lambda. Kind of looks like a bit of a XY hybrid with the Y flipped upside down. If you've played Half-Life at some point, you've seen that. So the other thing is we have a few more terms to deal with. So we have a wavefront. So a wavefront it's what we would call this imaginary line. It joins all the points that a wave reaches at some instant. So for example, if we're kind of looking at a wave propagating in time, so we kind of have this wave, it's going this way, this is its wavelength. This would be known as the wave front, these pink lines. This is just showing where the wave reaches at a certain moment in time. We're also going to talk about the concepts of incident and reflected wave. So a wave that we produce, or the original wave, this is what we're going to call the incident wave. If we're having a wave moving away from a barrier, like it hits a barrier and kind of reflects off that, that's what we're going to call a reflected wave. And if we link a bunch of waves together, this is a wave train. You're probably not going to see wave train come up too much. Now, one other thing we want to talk about is the motion of a wave, like the motion of points on a wave. Now, in my notes, I've sketched this wave in pink in advance just because I wanted to make sure I could sketch it clearly. The first time I tried to film this video, I didn't do such a good job, so I had to scrap the video. So here's a blue wave. This blue wave is a wave at, say, time 0, and this pink wave is sort of the wave at some time after 0. So the wave, we're going to say, is traveling to the right. Now, we might want to ask ourselves, what's happening to these points in the medium? The common answer that a student will want to give is, well, those points are moving with the wave. And you'd be fair to want to say that. It's very tempting. It's also incorrect. Remember that the points don't actually move in the direction of propagation of the energy transfer. They execute simple harmonic motion. So what's going to happen is these waves, they're going to sort of stay, these points on the wave, they're going to kind of stay in the same vertical plane. So at this point, time 0, this point A is here. But if we move the wave along a little bit later, you'll notice that if I keep in the same vertical plane, A is now down here. And then for B, if I move it down, B is also down here. So what you'll notice is that as the wave travels to the right, this point A, it's moving down. And eventually it's going to move back up, and then it's going to continue moving up and down, up and down. So A is moving up and down about this equilibrium. You'll notice that A and B are in the same kind of relative position on the wave. They move together. You'll notice that they both, after some time, move towards the same point, or towards the same point in time as the wave passes. What we would say is that points A and B, they're moving in phase with one another. And then we have the points C, D, and E. They are also on the same points of the wave relative to one another. We'd also say that they are moving in phase to one another. But that's the biggest misconception with waves. We'd want to say, oh, if the wave is moving right, points A and B, C, D, and E are all moving to the right. No, they are just executing simple harmonic motion about this equilibrium point. So in this case here, this is a transverse wave, which we're going to talk about later. They're moving up and down about this point. So as the wave passes through, A is moving down, and then eventually as the wave starts to pass through, it's going to move up again. So sometimes when we sketch waves, we will sketch them as ray diagrams. So you're going to kind of see the center of these circles, and then you're going to see these concentric circles outwards. So those concentric circles are meant to show the actual wave itself moving outwards, and then these rays are just meant to show the actual direction of propagation, like where that wave is heading. So because these waves are moving out from a point, we'd actually say that they're diverging rays. So on this diagram, when we're sketching the waves as these concentric circles, we're actually sketching the crests. The troughs would be halfway in between. So like the trough would be here, 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 here. So if you want to find a wavelength, for example, you could look at the distance between two successive crests, or you could kind of look at halfway between the distance between two successive troughs. Both of those will work just fine. Now, we talked a little bit about reflection, and waves do undergo reflection. You'll also learn a bit later that they undergo something called diffraction and also refraction and polarization. Those are things you'll look at in Physics 30. We're just going to stick to reflection. And reflection is something you've already done in science in a previous course. So just to refresh, if we have a ray coming in, it's going to reflect off of a surface. Now, if it comes in with some angle of incidence theta I, it's going to reflect with some angle of reflection theta R. What we know is that those two angles happen to be equal. So what we could say is that the angle of reflection is equal to the angle of incidence as in the same plane. So in the same plane just means like if it's coming in flat here, if it's kind of coming in this XY plane here, it's going to leave in this XY plane. It's not like the light's going to come in and then it's going to bounce out towards us, like come outwards like that. If it's in this plane here, it's going to come out towards that plane there. Now, having the law of reflection is great in words. We're just going to put it in the math terms. So theta I equals theta R. That's it. So one special case is if that angle of incidence happens to be parallel to the normal, so it comes in perpendicular to the surface, it's just going to reflect perpendicular to the surface. And that brings us to this thing called the normal. So any reflective surface, you'll see kind of this dashed line that's drawn 90 degrees to that surface. This line here is referred to as the normal line. We take all of our measurements relative to that normal line, and that's a really important point. The angle of reflection is always relative to that, so beware of that. So let's look at this example here really quickly. So we want to find the angle of reflection for a light ray on mirror 2. So here's my mirror. I'm going to first of all draw in my normal line. So this is my normal line, and this is going to make a right angle with this surface. So I know if this angle here is 40 degrees, then this is going to be the complement, which is going to be 50 degrees. So I have an angle of reflection coming in of 50 degrees, or sorry, an angle of incidence coming in of 50 degrees, which means that my angle of reflection also has to be 50 degrees. So we're going to have something that looks a bit like this. So we're going to have 50 degrees. And now what we'd like to do is we would like to find the angle of reflection off mirror 2. Once again, we're going to need a normal line here, and it's always 90 degrees to that surface. So this is my normal line. So I'm going to have an angle of reflection here. So I'm going to have some theta 2. I want to know what that is. Well, I know this angle here is 50, and we know this angle here is 40 degrees. Because again, this is a right angle, these are complements to one another. So you'll find a lot of these reflection questions, you're doing quite a bit of geometry. So I have this 40 degrees, and I have this triangle, because I have this triangle that's been formed here, and we know in a triangle the angles add up to 180 degrees. So I have 120 degrees here, I have 40 degrees here. That is going to tell me that this angle here has to be 20 degrees, which means that this angle here has to be 70 degrees. Now, if my angle of incidence on mirror 2 is going to be 70 degrees, that's going to tell me that my angle of reflection off of mirror 2 is 70 degrees. So by geometry, theta 2 is 70 degrees, or the angle of reflection off mirror 2 is 70 degrees. The important thing is that we're looking for the angle relative to the normal. So if you put 20 degrees, that's not right, because that's not relative to the normal. So watch for that.